In this video, we're going to be talking about heat transfer and how it relates to phase change, to melting and boiling and freezing and condensing. So most of all of what we've talked about so far is heat transfer and how it affects temperature. And that is the most common outcome of heat transfer happening, is that the temperature of your substances changes. And temperature changes because kinetic energy has changed. So most often, when heat transfer occurs, between two different substances, it's the kinetic energy that changes. And we measure that as a change in temperature. So one thing gets warmer, one thing gets colder, they meet somewhere in the middle as a thermal equilibrium is established. But that's not the only thing that can happen. And this is where the issue with associating the word heat with temperature becomes problematic, because heat transfer can occur without any change in temperature of your substances. So there are essentially two options: that when heat transfer happens, either the kinetic energy of your substance changes, which we measure as the temperature changing, or the potential energy can change, which we observe as a phase change, as melting or boiling or freezing or condensing. So heat transfer can also affect the potential energy of a substance. Which does not change the temperature. So when this occurs, when potential energy is what's changing, is when we're undergoing a phase change. From solid to liquid, or liquid to gas, or gas to liquid, or liquid to solid. So solid to liquid we call melting, liquid to solid we call freezing, liquid to gas we call boiling, gas to liquid we call condensing or condensation. So when we are melting something or boiling something, that requires an input of energy. Melting and boiling are endothermic. You have to put energy in order for those processes to happen. So delta H for these is positive, We say they're endothermic. In order to melt something, to turn a solid into a liquid, you need to disrupt some of the intermolecular forces. You need to pull apart some things that are attracted to one another, and you have to put energy in order to do that. Same idea when you're boiling a liquid. You are physically separating all of your molecules when you convert them from a liquid to a gas. So you are essentially pulling apart all of your intermolecular forces in the boiling process. Those molecules were attracted to one another and you're trying to pull them apart. You have to put energy in to do that. So melting and boiling require that you put energy in. So the enthalpy changes for melting and boiling have special names. So for melting, it's known as the enthalpy of fusion or the heat of fusion. Symbolized delta H fuse. It's usually called the heat of fusion, sometimes called the enthalpy of fusion. Those two terms are used interchangeably. So this is the amount of heat required to melt a particular amount of substance. Usually expressed as either 1 gram or 1 mole. So you would need to look at the unit that was given to know which one you were working with, but it's always heat per some quantity of stuff. For boiling, same idea. We have a delta H known as the heat of vaporization, delta H vap. Also sometimes enthalpy of vaporization. Exact same definition, except we are boiling instead of melting. So it is the amount of heat required to boil 1 gram or 1 mole of a substance, depending on what unit it is given in. So these values vary from substance to substance, but what they all have in common is that they are all positive. Also, less important, but interesting to note, for a particular substance, heat of vaporization is always larger than the heat of fusion, and that's because of what's happening at the molecular level when you boil a substance, that you are really overcoming all of the intermolecular forces when you boil something, as opposed to melting is only kind of loosening up a few. So there's less change at the molecular level, really, between a solid and a liquid, so it doesn't take as much energy than completely separating all of your molecules to get to a gas. So boiling requires more energy. So if melting and boiling require an input of energy, that we have to put energy in order to separate our molecules, when we go in the opposite direction, when we freeze or condense, we're forming new intermolecular forces, which means we get that energy back out. When a new bond forms, energy is released. So freezing and condensing release energy. Which means that delta H for these are going to be less than 0. They are exothermic processes. And these don't actually get special named delta H values because they're just equal and opposite to the ones we just talked about. So freezing and melting are opposing processes, are opposite processes. So for freezing, we just use negative heat of fusion. So we take whatever we had for melting and we throw a negative sign in front of it, and that is the enthalpy change associated with freezing. It doesn't have a special name, it's just the negative heat of fusion. And same idea for condensing. We just take the heat of vaporization, the one for boiling, and toss a negative sign in front of that. So as heat is continually added to a substance, what you're actually going to see is that it alternates between changing the kinetic energy and the potential energy. That if we're starting with a solid, your temperature will increase up until the melting point, and then your temperature stays constant while it undergoes the melting process. Then once it is fully melted, the temperature begins to increase again in the liquid state until you hit the boiling point, and then it boils while the temperature stays constant. And then once it's all a gas, the temperature begins to increase again. So we can represent this graphically with heat added to our substance in joules on the x-axis, and the temperature, say it's in Kelvin, on the y. So what we would see is that if we're starting very, very cold here, that the first chunk of heat we add, our temperature increases gradually until some point where it levels off for a little while. Then our temperature begins to increase again. Until it reaches some point where our temperature stays constant, even though we're continually adding heat. And then it increases some more. So if we just kept adding heat and kept adding heat and kept adding heat, we would see a line segment like this that essentially has, or a line like this that has 5 different segments to it. So we have, let's make this bigger. This first area here where our temperature is increasing as we're adding heat. So what this first segment represents is if we're moving left to right, we're heating our solid as we move in this direction, which is kinetic energy is increasing as heat is added. The next portion we see here levels off, that even though we're adding heat, we're moving along our x-axis, it is horizontal, our temperature is not changing, that remains constant. So in this portion of the graph, what's happening is that we're undergoing the melting process, that our solid is converting into a liquid. If we're thinking about this in the add heat direction, we can also think about this in the other direction, in which case this line segment would represent freezing. But if we're thinking about adding heat in, we would be melting. When we melt something, is our potential energy increasing as we're adding heat in this portion of the graph. Then as it begins to slope upwards again, it means that we have converted our solid now into a liquid, so the temperature can begin to increase again. So this central portion here is where we're increasing the temperature of our liquid. As we add heat in, if our temperature is changing, our kinetic energy is changing. So this is the kinetic energy increasing as heat is added. Then we come to some certain temperature where it levels off again. That temperature is our boiling point. So as we're moving across this portion is where our substance is undergoing boiling. So we're boiling our liquid as we add heat, converting it into a gas, which means that it is the potential energy changing as heat is added in this region. And last but not least, once everything has been converted to a gas, the temperature will begin to increase again. And any additional heat will go into heating up that gas, increasing its kinetic energy. And all substances will have a very similar looking graph to this. They'll have these 5 segments where you can increase the temperature of your solid and then it melts, and then you can increase the temperature of your liquid and then it boils, and then you increase the temperature of your gas. So they'll all have something very much similar to this. So we've already talked about how we handle temperature changes. So when the temperature changes, we know how to calculate how much heat is involved in that. We have our equation Q equals mc delta T. So when our temperature is changing, we can use this to calculate how much heat was involved in the process. But during the melting and boiling portions of the graph, we can see that we're adding heat, but we're not changing the temperature. Delta T is 0. So if we try and use this equation, delta T is 0, Q comes out to be 0, but we can see on the graph that it's not. That we are moving along the x-axis as we melt, despite the fact that our temperature isn't changing. So we need a different equation. We need a different way to approach mathematically how we calculate the amount of heat involved in a phase change. And all we really need is those enthalpies that we talked about earlier. So we're going to be using the heat of fusion or the heat of vaporization, depending upon which phase change we're talking about. So this isn't so much an equation as it is just the definition of those things. So heat of fusion or heat of vaporization, delta H of anything really, is just the amount of heat per mole of substance or the amount of heat per gram of substance. So these values for heat of fusion and heat of vaporization are constants that you would be given or you would be able to look up at any point in your life. You would know the amount of substance that you're using, so you can solve for Q, just using the definitions of these enthalpy changes for the different phase changes. So to use these, we can just essentially solve these definitions for Q. Is delta H times moles, or depending on what information you're given, Q times mass. Oops, I did this wrong. Q is delta H times mass, or delta H times moles, depending on the unit that delta H was given in. But either way, we can use those to solve for the amount of heat involved in a phase change process. So this allows us to determine how much heat is required to melt or boil or freeze or condense a particular sample. So for instance, we can figure out how much heat is required to melt 15 grams of water at 0 degrees Celsius. So 0 degrees is the melting point, so there's no temperature change occurring here, just the phase change, which means the only piece of information we need is the heat of fusion as well as how much water we're melting. So the heat of fusion here is given in joules per gram, which is cool since we have the mass of our stuff. So to find the amount of heat, we just need to take the heat of fusion times the mass of our stuff. We're given the heat of fusion as 334 joules per gram. We're told that we're working with a 15-gram sample of water. So we can determine that it's going to take 5,010 joules of heat to melt that sample.